Hi, this is Professor Guyad again with Middlesex College, and in today's lecture, we will be covering recursion. Recursion is a very important concept in computer science and programming. It's the idea of a function or method, same thing, right? Function method that calls itself, right? So in a recursive function, you have what's known as a base case, which will stop the execution of the function and spit something out, return something. And you will have a recursive case that will keep the execution of the function going. So you can have numerous base cases and you can have numerous recursive cases. In the examples that we'll see, there will just be a couple. So we won't get too complex, but these recursive functions that we're going to cover are so essential, again, to understanding more complex cases in recursion. So let me share my screen as usual. So we have our Visual Studio Code. We have a class called Recursion Lecture. And we're going to write a couple of recursive functions. So recursion, another way of seeing it is it's kind of like a loop. So what I want to do for this first recursive function is rewrite a for loop that would calculate the sum up to a given number, a given integer. So let's do that. So um, recursive function one, calculate the sum up to a specified integer. So we're going to call that, we're going to say public static. And of course, it's going to return an integer, right? Because a sum of integers is an integer. So, the sum up to, so if we said like the number 5, we want to add 0, 1, 2, 3, 4, and 5. They're all integers, so the sum of all integers is an integer. So the return type is int. I put the static there, the static keyword, because static just means we don't need to declare an object. We don't need to instantiate an object to call this function on. That's what static means. We can just call the function without creating an object. So public static int, the return type is an int, as I just described, and then we're going to call it sum. Simple. The arguments, the parameters that it's going to take are the sum that we're going to keep adding to and the number that we're adding up to. So we can just call that I to keep consistent with a for loop, right? Like how we use the number I, the variable I. So let's see how this is going to look. And it's only red underline because it's waiting for a return value of an integer. So I'll just put that there so we don't have the red underline. Okay, so let's get into this. What would this look like? Well, we know that inside of a for loop that we were adding I to sum each time. We could write the first line as sum plus equals I, right? That's the most important, not most important, but that's the kind of main thing we're doing in this function, right? Adding each integer I to sum so we can get a total. And then here's our base case, which again halts execution of the recursion. So the base case would be something like if so if you want to think about this, like if we're starting at the number like 5, like I mentioned previously, and we're going to decrement I by 1 each time, then it makes sense to stop I at what integer? You got it, 0, right? So if I is 0, then we want to return the sum. So that's our base case. That's going to halt the execution. Once I is 0, we're going to return the sum. And then The recursive case, so I can write the recursive case here, which is the part that keeps calling the function itself, is going to look like this. If no, I don't even have to write an if. I can just do return the function name sum and sum, right? Because we're just working with the sum that we've accumulated after so many iterations. And then what are we going to change about I so that we don't get a quote unquote infinite loop, right? We don't want an infinite loop. So we have to change the value of I. And I mentioned it earlier, we're going to decrement I by 1 each time. So yeah, and then I don't need this any longer. So this is what a recursive function could look like that added up the numbers up to a specified integer. So if I go to, public, right, we know this function so well now, main, right, and I test this function. So I call, because it's static, I can just do sum, and I can do 0, right, because the sum should start off as 0. I'm going to hard code 0 there, and I'm going to count up to the number 5. And we like to predict what the output is going to be. So expected output. So what's 0 plus 1 plus 2 plus 3 plus 4 plus 5? It should be 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus, so 15. And I want to, because it's returning sum, it's not actually going to print to the console. So I have to wrap this in a system.out.println. Okay, and we're going to test this and we're going to see how it worked. First, we want to make sure that it works correctly. And yeah, that's indeed, we got 15. We got our expected output. Awesome. So we know it's working. Let's just trace execution now. Tracing execution, right? It's so important. So we go, so yeah, so the Java program, the compiler starts in main and it prints this function, sum 0 and 5 is the parameters. So sum 0 plus equals 5 is 5. And then is I equal to 0? No, I is 5. So we don't return the sum yet. And then we go here to the recursive case and we see sum is now 5 and I minus 1 is 4. And we're calling this function again, sum. So then now these parameters become 5 and 4. So now sum is 5 plus equals 4, 9. And then is I 0? No. So then we call sum again with the parameters 9 and 3 now, because 4 minus 1 is 3. So ... will eventually get to sum is 14, okay, and I is, or sum is 15, sorry, and I is 1, and 1 minus 1 is 0. And then we'll put sum, so 15 plus equals 0 is 15. And then is I equal to 0? Yes, true. So then we return 15. And that's why this printed out 15. Awesome. Now let's do a more complex, but still understandable, common recursive function called the Fibonacci sequence. So number 2, Fibonacci sequence, you specify a term in the sequence and you get the sum of the prior 2 terms. So working through this, we can do public static. It's going to return an integer, right? Because the Fibonacci sequence, and here's how the Fibonacci sequence looks. So the first term is 0, the second term is 1, and then the third term is the sum of the prior 2, right? So 1, and then The fourth term is the sum of the prior two, so 2, and then 3, and then 5, and then 8, and then 13, okay? So we see that the return type, again, is integer, so int, and then we'll just call it fib, for short for Fibonacci sequence. And the only parameter we need is the term specified that you want to return. So int I is fine, or we could call it int term. Either one is fine, but I'm going to just go with I. And then here we go, and we have to think about the base case. There's 2 base cases and 1 recursive case. So if I is equal to the 0th term, which is 0, or if you want to think about it as the first term, I equals 1. So if I is the 0th or first term, let's return 0, right? Because 0 is the first term. You see this right here? Or the 0th term. We can think of it in both ways. Else, if I is equal to 2, then the second term, the second term is 1, right? So we should return 1. So these are our 2 base cases. Then the recursive case is the sum, quite literally, we're going to code the pseudocode is, right, the sum of the prior 2 terms. So how does that look? We're going to do return fib, and remember, it's a recursive function, so we have to call the function itself. So return fib I minus 1 plus fib I minus 2. So we get exactly what we need. So this is how the common and popular Fibonacci recursive function looks. So let's copy this, paste, call this fib, and it only takes 1 argument. And let's say we want so what's 8? 8 is the 1, 2, 3, 4, 5, 6, 7. So 8 is the 7th term. So I'm going to put 7 as the argument, and our expected output is 8. So expected output is 8. And let's run this to make sure it's working correctly. And that's exactly what we got. We got 8. So we know that our fib function, recursive function, is working. So we can trace this. So let's start with as if I was 3. Let's go with the third term. So 1 is the third term. So if I is 3, is 3 equal to 0 or 1? No, false. Is 3 equal to 2? No, false. So we go into the recursive case, and what's 3 minus 1? 2. So, and then 3 minus 2 is 1. So let's do fib 2 plus fib 1. Let's see what that looks like. So fib 2, oh, look at that. I equals 2. So 1. So this right here essentially is, when I starts out as 3, this part is essentially 1. And then 3 minus 2, what's fib 1? Oh, right here. When I is 1, we have 0. So what's 1 plus 0? 1, right? And then to get to I equals 7, we just keep building off of that. So you can see how it mimics, in a way, a loop, right? We just keep building off of the recursive case until we get finally to the base case, or base cases, one of the base cases. Great. So let me stop sharing. So we have just seen recursion in action. Recursion being similar to looping, a little bit different, and noticing that tracing our recursive functions really helps in understanding what's going on. And the notion of the recursive function, one more time, is that we have a base case or cases that will halt the execution of the function, the recursive function, and spit something out, a value, and the recursive case, which calls the function itself to keep execution going until we get the desired output. So again, this is Professor Guyad with Middlesex College, and thank you for following my lecture on recursion.